Hello, this is Robert Casey, and this presentation will be about YSNP prediction via YSTR signatures. So what exactly is YSNP prediction? YSNP prediction takes values of YSTR values and predicts whether you will test positive for a particular YSNP or not. Testing should always start with 67 marker testing, followed by many various options for YSNP testing. YSNP prediction saves you testing costs because it avoids having to do unnecessary YSNP test due to knowing its prediction. There are some basics behind YSNP prediction that you need to understand. YSTR testing is one kind of YDNA testing, where YSNP is really a different kind of YDNA test. They're somewhat independent, but this data does track each other. From a mathematical term, this means the data is actually correlated. YSNP prediction takes patterns of shared YSTR mutations, and based on those shared mutations, predicts YSNP branches from these patterns. This prediction methodology works best in the 1200 to 2500 year range. The math behind this YSNP prediction is called binary logistic regression. This is a statistical model. YSNP prediction uses two variables. It uses the number of YSTR markers that the tester matches the YSTR signature, and it takes the genetic distance of the tester from the YSTR signature. Based on those two inputs, it'll come back and give you a prediction of a percentage from anywhere from 1% to 100%. With min and convergence, prediction is usually above 99%. So you get your 67 marker test back. Here is an output screen, but by itself it has no relevant meaning. All it shows you is your marker values. It only has any kind of context at all when you compare it with other testers. Using the FTDNA Matching System, it takes a potential tester and shows you all your matches. On the far left of this column, you'll see genetic distance varying from 0 to 7. This is a very good example of how and when family tree matching system works. All these are cases. There's a couple of a Hanvey and a Meredith, which are probably NPE events, and then there's Kersey, which is probably a surname derivation issue. But in this particular scenario, the family tree DNA matching system works quite well. But the family tree DNA matching system has issues. First of all, it only matches people who are genealogically related, and their definition is 1,000 years. This is too young of a matching system if you're trying to do haplogroup research in the 1500 to 25 year range. The system assumes a normal distribution, but in reality, data is skewed. It has tails, which are the flares of a bell on the bottom. Also, there's a lack of divergence under haplogroups, which can result in 50 to 90% error ranges versus the advertised 5% error rate for 67 markers. Shared mutations are a better approach than how many markers that you don't match. YSTR signatures show that mutations that you share. This is just a much better approach. Using YSTR signatures, you can predict haplogroup, and then with additional YSTR testing, you can actually chart the connections. Matching by genetic distance is flawed and has many issues. You need both STRs and extensive YSNP testing to determine true relatedness. The best way to understand is to visually see a YSTR signature developing. In this chart, I have eliminated about half of the columns and about 90% of the rows. But if you look at for any kind of consistency of color across this chart, which is the purpose of this chart, the blue just jumps out at you. And that's what the basis of signatures are. And if you look at this column, these are all 11s, but why are they blue? It's because up here on L21 is the an older haplogroup that we're comparing L226 to. L21 is predominantly like 95% 12, but 95% of L226 is 11s. So that's a mutation from 12 to 11. This and 9 other mutations, which are different from the L21, is the signature of L226. There is a definite order to testing that you should conduct. First of all, the first test you should test is a 67 marker test. I do not recommend the 37 marker, even though it does have its usage, because you can't chart. And we all, as genealogists, want to be able to chart our connections. 37 is not enough resolution to do that. You next need to determine your predictable YSNP branch, which is around 1200 to 2500 years old. That way you need to know what part of the haplotree that you belong to, so you can start comparing people who are similar to you because they share a haplogroup. You then start extensively YSNP testing, which allows charting with a combination of YSTRs and YSNPs. This chart shows the ultimate goal. It is a chart of a branch under L226. It is DC201. This is one of your ideal branches because everybody under DC201, all but one, is a McGraw or McCraw or McGrath, which are all surname variations of each other. So you have 18 people and only one, Milam, who is probably an MPE event. But this not only gives you an indication that if you test DC201 that you belong to this genetic cluster or surname cluster, you do have branches developing based on STRs. You have 2 larger branches, the one on the left with 2 additional STRs that create one big branch, and then another branch that only has 2 testers. That's an older branch that has 2 other testers. Then under this larger branch you have 2 other branches. So you have a total of around 4 branches that have developed. With more YSNP testing and more 111 marker testing, you could easily double the number of branches to see exactly how all these particular testers are related to each other. There are many other forms of YSNP prediction, and I'm only going to briefly cover them here, but this presentation is basically going to be dedicated to 2-variable binary logistic regression. For very old SNPs like RM269, there is another math-based approach that can get you to branches, but these branches are, several thousand years old, anywhere between 5,000 and 10,000 years old. They do sort out a lot and separate you from other parts of the world, but since around 80% of all English-speaking people are RM269, it only eliminates 20% of the people that people in the United States are generally interested in. There is another extension of this, which is Bayesian allele frequency technology done by a company called Navgen out of Serbia. And this is a very accurate, and this next Navgen extremely closely matches binary logic regression. But the problem with this technology is it cannot be visualized, or it can't be ported to Excel in forms of macros. But this goes to show you that there's more than one way, mathematically, to derive at answers. Even charting, which is a level below YSNP prediction, it also involves YSNP prediction components as well. There are 2 forms of binary logistic regression for this particular application to genetic genealogy. Most people only use the signature And this still works with 90 to 95% accuracy, which is pretty good accuracy. But an improved model uses both signature and genetic distance, which increases the accuracy to 99 to 100%. So there's just no reason not to use a two-variable model. Both can be visually displayed and both can be ported to Excel and forms of macros. Here's an example of a signature-only prediction. It's quite simple. This is for RM222, which is a very large haplogroup, and it has a very large signature 11. To date, there's been 200-300 testers that have tested positive, and several thousand have tested negative. And everybody who has a signature match of 5 and less, they've all tested negative, and all the ones that have tested for 6 or higher have all been positive. So this is a very accurate model and works quite well, but not all haplogroups are this clean. Here are some issues with the signature-only approach. First of all, there's a lot of overlap of signatures all throughout haplogroup R. So you must have confirmed RL21 in order to have that chart. So that's a $99 expense, which if you add a second parameter, you no longer need to take this qualifying test. So this is a better methodology because it saves testing costs right up front. Also, there's a bug in all statistical software packages that do not like perfect curves. The way these regression formulas work, if it's a perfect curve, it can't arrive at the constants because it's too perfect. And there are very high-end packages where they throw a little noise into them, but these packages cost a couple $1,000 plus several $100 a year, plus several $100 for version upgrades and maintenance cost of $100 per year as well. So these are quite expensive packages to solve an issue that is really can be solved by adding a second variable. It also does very poorly for boundary condition testers. And boundary condition testers are very important because these are the ones that show the very early formation of haplogroups and can reveal a lot about the geographic origins, what actual STR values started out with, and those kind of important issues. So adding a second variable does reduce the error rate by 2 to 10 times. But that's not, it doesn't affect too many people. So if you're talking about 100 testers, going from 95 to 99% is that it predicts 4 more testers. So that's not that many, but there again, it's a 2 to times increase in accuracy and should be used. Here is a chart that shows a empirical way to do both signature and genetic distance prediction. This requires no math, no statistical packages, and can be done by anybody. First of all, the first column is signature matches for L226 again. It goes from 9 to 5. The second column is the maximum genetic distance to test positive for each of the signature matches. So you have at signature match of 9, the highest to test positive to date is 10, and then the other values. And then at 5, nobody has tested positive today, so it has none there. Then you also look at the minimum genetic distance for any negative testers. There are no negative testers at 9 because it's genetically isolated to a point to where there are no testers that overlap. But when you get down to 8, there are starting at 26, which is a pretty high genetic distance. You start finding negative testers, and as you go down, the number of the genetic distance continues to decrease to test negative. So it makes common sense that you will continue to test positive somewhere in between these two, for the second and third column. So the genetic distance filter is to take an average of these two, and where they don't exist, just double or divide by 2 or multiply 2 to get allow some variability. The last column shows you some boundary condition testers that could change your formulas, the constants in your formulas. If you look at the signature of 6, there is one tester at a genetic distance 11 that has not been tested. Since that's a pretty high signature max, that won't have too much of an impact. But if you go down to a signature max of 6, we currently have the highest of 8. Going to 10 would probably make a pretty significant difference in the constants. And then there's one tester at a signature match of 5 that's only a genetic distance of 6. If that person actually tests positive, that will have a fairly radical effect on the constants. This is just taking the table and converting it to graph form to give you a more visual understanding of how this technology is working. First of all, the bottom line, which has the little diamonds, that's the maximum positive genetic distance to test positive. So the binary logistic regression will basically fit a curve to that one. And then the ones with the triangles are the lowest genetic distance to test negative. So you know that somewhere between those two lines is where the actual line is, and that's what I'm calling a genetic distance filter. And this line is probably a more likely curve of actual testing positive. There are issues with YSNP prediction. The biggest issue is not actually generating the models. That can generally be done in 5 or 10 minutes. It does take a little time to learn statistics and you download a statistical package, but it's very minimal time. The time is obtaining the data, which is very challenging. With various privacy issues of people not joining any projects, setting their values to privacy themselves. Project can set certain kind of reports to privacy, and there's just way too many ways to lose data through privacy. Also, you have more than one vendor. You have Y-Sequence and Full Genomes as other vendors, as well as Nat Geo tests, which are not recorded, and all kinds of other tests that could be integrated. And then you just have missing data. For family tree DNA, there are no reports for big Y. So we have to create our own databases for big Y data, which is really a very challenging thing for many parts of the haplogroup, haplotree. Also, one unknown is you got to learn statistics a little bit. It's not rough stuff to learn, but a lot of people don't want to dive that deep into the math aspect. And you got to have a statistical package to generate the constants. But you can get one for only $20. Accustat does generate good constants. Unfortunately, the accuracy measurements is a little lacking in this particular product. There's also forms of convergence that can greatly lower the accuracy of prediction. So as you do more and more YSNP prediction, you'll get very familiar with convergence. And also there is boundary condition testing bias. People who have a lot of high genetic distance on very poor signature matches just don't want to test, and so you got to figure out a procedure to get these people to test. The ultimate goal is charting. Charting really requires good accurate SNP predictions so you can locate all the valid data very quickly and readily. Charting itself is also based on binary logistic regression and signatures, but there are some important variations and these will be covered in follow-up presentations. The origins of haplogroups really need binary logistic regressions to find the boundary conditioning testing, because those are the ones that can really reveal a good information about the origins of haplogroups. And also, you need extensive YSNP testing. YSTR testing by itself is just fraught with all kinds of issues. Okay, I'm going to dive a little bit deeper into the math. So the people who don't want to get math, you can bow out at this point. It's not real rough stuff, though. This is just giving a high-level overview of all the assumptions and some of the details of macros that are used in Excel. This part of the presentation shows you step-by-step statistics that support YSNP prediction. And I'm only going to cover the two variable predictions since this has much higher functionality. As anything, you have critical assumptions, and these are discussed, and I actually will show you the actual equations and the macros for Excel spreadsheets that you can use yourself. The first topic is the exclusion criteria. All studies of mathematical models have exclusion criteria. You don't have to test everybody in the world or have all the values of every single haplogroup to be included. So anything that's not connected in the last 10,000 years, such as not being haplogroup R, you can filter out all those if you're analyzing a haplogroup under R. It just simply does not make sense to include the whole world's haplotree when there's no chance of it being related to you. And also, there's no need to verify L21 anymore because with two variables, the genetic distance acts as a filter to get rid of all the overlap of signatures. Since there's never been any signature with 7 or more that's ever tested positive under 50%, there's no need of including all the negative values for 95% of the negative testing under haplogroup R, because you just don't need to include it because it has almost no effect on the constants. So that gets rid of 90% of the negative data, which greatly reduces the labor in creating the data input. And also extremely high genetic distances. If you start out with negative genetic distance, testing negative at 15, it goes to 20 to 25, 30, and they're just a truckload much higher. It just doesn't make sense to analyze all this extremely high when you already had 50 to 100 testers that have tested negative up to 30. So that rules out another 75% of the remaining negative data. It's filtered out because it's just not relevant and it's not worthy of the time to analyze. And then you have to have a criteria for outliers. In our case, we do have 2 outliers, and these outliers should be excluded from our models because they are not typical and do not behave like the normal mathematical models. One is a massive relock event. This is a situation for most of your multi-copy markers. They're in the palindrome region, which is a big loop. And because this loop on either side looks very similar, sometimes they actually recombine. And so you don't have your normal YDNA evolutionary, you actually have a little minor recombination. If you have a lot of potential multi-copy markers in play, these can significantly throw things out. So, but these are extremely rare. These are like, 1 out of 5,000 events. But when they do occur, you need to, 1, not include them in the input stream because they would really throw off the model. And 2, you need to understand that these can test positive and you need to be on the lookout for these special events. Also, not all SNPs mutate just once. Some of them are very useful that have multiple independent mutations across the haplotree. And so if you use these particular YSNPs that have multiple mutations, they can be extremely useful within your haplogroup. But when it comes to model time, if you include all of R, you may find a couple of independent events of this mutation, so you got to filter them out in a rational manner. Any discussion of statistics wouldn't be complete without a discussion of bias. And there is a significant bias in testing. People who have high genetic distance and very poor signature matches, they're on the borderline of boundary conditions. They just don't feel like they have a good chance of testing positive, and they check out. And haplogroup administrators need to reduce this bias by either sponsoring their testing or explaining the benefits and showing them mathematically that they do have actually a pretty high probability of testing positive. Any statistical study also needs to take the impact of sample size. Statistics require anywhere between 10 and 70 testers per variable. So since we're using two variables, signature and genetic distance, we should have somewhere between 20 to 140 testers before the model will yield accuracies. In this scenario, this is definitely way towards the 20 range and not net. You don't need 140 to get very high accuracy. But this is something that you need to take consideration. If you go ahead and do it with only 10 testers, it could be pretty accurate, but you need to be on the lookout that your constants will change in the future, and the accuracy of your model is not really going to be accurate once you get a higher sample size. Also, the sample size varies dramatically between haplogroups of the same age. Some were lucky to have conquered all their neighbors and enjoyed the benefits of the conquest, and others were conquered and barely survived. So haplogroups being prolific are on the leading edge of this, I guess, discovery. And so the ability to predict will vary significantly depending on which part of the haplotree and how prolific, i.e. how big your sample size would be. And always remember, accuracy always increases with an increased sample size. So it is important to have as much data as possible. We do have one genetic factor that does not fit into the mathematical world. It's called convergence. Convergence is a genetic phenomena where if you have no convergence at all, you can have unbelievably powerful accuracy. The vast majority of the time, it is exactly 100%. I mean, 100% accuracy. Also, SNP prediction also works with very modest conversions. So if you just have a little bit, you can still get 100% accuracy. And if you have a little bit more, you can get down to 95% accuracy. But if there are significant conversions between your haplogroup and older haplogroups, you're just not going to get a good model to fit. And you may need to go to 111 markers or even 500 markers to actually be able to do SNP prediction and isolate yours from others. But this is a very small minority of people that have this degree of convergence. Hold on, here's the actual equation. It's the top line, which is a pretty long line. And I'll try to break this down as easy as possible. Y, the term on the left, is the prediction amount. It varies from 0 to 1. So if you want this in percentage, you got to multiply this whole number times 100. E is called Euler's constant. It's similar to pi. It's actually a mathematical formula to come up with this number, and it's used in thousands and thousands of scientific studies. And it's just a number that works for unknown reasons. If you see two asterisks, that means take the power of. Take the power of means if you have 2 to the 2, that's 2 times the second number is the power of, and the number to the left is what you're multiplying. So 2 to the 2, 2 asterisk asterisk 2 means take 2 and multiply it times itself times 2. If you take 2 asterisk asterisk 3, that means takes 2 and multiply it times itself times 3 times, and that would be 8. So it's the exponential is what that means. Asterisk just means multiply. And then the constants A, B, and C are the constants generated by the model. And then the statistical package. And then sig is the signature, and G is the distance, which you have to calculate through macros. This is showing how well this ports to Excel. all you have to do is take this particular macro, copy and paste it out of the spreadsheet, out of this presentation, or hand key it in, and boom, if you have your signature and genetic distance, this is the formula for L226. But you do have to, and cell K19 and L19, you have to have the signature and a genetic distance in those cells. And those are just another set of macros. You only have to do this for one tester, and then once you create the signature and the actual haplotype to compare for the genetic distance, you stick those into the first row, and then you just copy and paste these rows through all 200 others, and they all automatically update. There's only one entry, and then every time you run a model for a different haplogroup, you obviously have got to change the constants as well. There are issues with binary logistic regression, even using two variables. It's kind of disappointing that an empirical model still seems to have better accuracy than a very highly sophisticated model. So the model just seems binary logistic regression doesn't try to take an average between the extreme of the negative boundary and the extreme of the positive. It just shows you the positive boundary. That's it. It doesn't attempt to look at untested data in any manner at all. New boundary condition testers, as they come in which you find one in between the existing and one tests positive, this will cause either your accuracy to go down because it'll miscall one or two testers, or it requires you running the model again with a new boundary condition tester to get your new constants. This is a chart where I decided just to go back in time and look at all the boundary condition testers and how they change the constants. I first started out in November 09, and that would generate the first set of constants. Then in September 2014, we had a pretty radical change. We had our first tester that only matched 6 and 9. This is the first signature match of 6 to test positive. That made a big difference because it's such a low signature match, and it's the first one, that obviously would have a major impact. Now all it did is predict one more tester at about 200 positive correctly. So it increased by changing these constants, it changed it from 99.5% back to 100%. In November 6, 2016, we had a very modest change. This is a higher signature match of 8, and the genetic distance was 8 to 9, so it didn't have much of an impact. In November 2016, in the late portion of that month, we targeted another tester, and that tester was the second tester to test positive with a signature match of 6, but this time it is a genetic distance of 8 instead of 6. And that had a radical change as we suspected. There again, this actually took in, brought our accuracy back to 100% for testers, but it also had a significant impact of taking a couple other boundary condition tests which were 0 and gave them small but reasonable amounts of percentages of actually testing positive. Then February of 2017 went from 9 to 10, the highest signature match of 9, which is the maximum you can match. It just has almost no effect at all to have a small increase in genetic distance with your highest signature matches. Then in November of 2017, we targeted another person to test, which was pretty speculative. He was at 7, but instead of the highest to test positive so far was genetic distance 8. This guy was 13. He tested positive, and he made a big difference. This is probably the biggest difference in the change as far as other boundary condition testers, as they many of them rose from 0 to the high 90s, and some are still down in the 10 and 20% range. But this goes to show you the importance of testing these boundary condition testers. We still have boundary condition testers that we've not located enough to, or encouraged them enough to test yet. One's at signature 8, that's only one below the maximum, and he's going to 10, 11. That would only have a minor impact on the constants probably. We have another one at 7, which is that's the lowest where signature match where there's a lot of people, and going from 13 to 15. Since that had such a high impact last time, that might have a fairly significant impact as well. There is another tester at GED 10 at signature 6. We think that would have even a more radical effect. And also, we're constantly finding new boundary condition testers which have higher yet higher genetic distances at signature matches than the current ones have. Here are 5 haplogroups that I've had time to analyze this, and I only started doing this at two variables in the last 2 or 3 months, and I will expand this list over time. But the real encouraging thing about this is look at this. If there's no convergence or minor convergence, they're all sitting at 100%. This is very encouraging. That it used to be in the 90 to 95% range, so this is a big step forward. And then I did pick one that had significant convergence, and it was only at 94% accuracy. In the past, that had probably been 70 or 80% accuracy. So this is really helping out haplogroups that have a fairly significant amount of convergence present. This just gives you a little information on how big the scope of these SNPs are and the signature size associated with each of these. L226 is a very large group, so we have 320 positive testers confirmed to be L226 and a fairly robust size of 9 signature matches. 7 is about as low you should go on a signature size. It doesn't really seem to make any difference that CTS 9881 has 14 signature matches. That might help you figure out a match manually, but once you get to 8 and 9, it seems to be okay. And it shows that L555 and L371, neither one of them have any kind of significant convergence, and they have 100% accuracy, even though the sample sizes are only 40 and 50 approximately. And the one with convergence only has 32, but there again, it's accurate enough to be very useful in making testing recommendations. There are some significant challenges with YSNP prediction. Collecting the data is extremely time-consuming. The amount of time that I spend collecting the data and the amount of time I spend with statistical packages is always a minimum of 10-to-1 ratio. It only takes 5 or 10 minutes to run the model, and it takes a lot of time to collect all the data. Also, because of convergence, it's you have to sometimes go look and analyze a haplogroup that's in the right time frame, but due to the convergence, isn't going to work or have much lower accuracy than you want. And so this convergence throws a major monkey wrench into the time involved to do YSNP prediction where there is convergence. And also the scope of some SNPs are just not that large. I mean, even though the ones I gave you examples of are 30 and more, there are hundreds and hundreds of haplogroups that could be predicted. They only have 5 or 6 or 10, which could be predicted, but accuracy may be a little questionable. But there are just so many of them that it takes a lot of time to do SNP prediction across the whole haplotree. So we need some kind of automation that would recognize the signature, recognize convergence, and automatically generate all this data. And that would be some pretty sophisticated software and would take quite a bit of time to develop. But there is a very bright future with YSNP testing. Most smaller SNPs are starting to roll up and become parts of slightly older haplogroups. So on one area, you have a consolidation of newly discovered YSNPs that allow you to predict at one level, so you don't have to predict 5 smaller ones. So it is improving in that landscape. And also, there's many haplogroups now getting to be hundreds of testing candidates, and so these are the more fortunate to have that prolific haplogroups. Not everybody falls in that category, but every day there's more and more YSNP branches that are crossing the 50 to 100 testers, which make ideal candidates for SNP prediction and charting. Also, YSTRs are widely known now, and they're used to not only to sort out how you're connected, but also it's being used for SNP prediction very widely as well. So all this does is reveals the math behind how signatures really work, and we're having very reasonably accurate charting now. It's becoming a reality. Under L226, I'm now able to chart 85% of the testers due to extensive YSNP testing. And that will probably go to 90% by the end of the year.